In the first part, we covered the legal side, the product liability, the machinery directive CE marking, and the ABC structure of the safety standards. Today we will get to the engineering core of the book, chapters 4, 5, and 6. That means safeguard, the physical and the sensor-based protection on the machine, safe control technology, the standards ISO 13841 and IEC 62061 that defines how reliable a safety function must be. And finally, safe communication, how safety signal travel dependably across industrial networks. Let's dive in. Every protective measure begins with the risk assessment, defined by the Type A standards ISO 12000 1000. The process is systematic. Determine the limits of the machine, identify the hazards across its whole life cycle, then estimates and evaluate the risk for each one. Risk reduction then follows the famous three method in strict order. Step 1, inherently safe design. Eliminate the hazards or reduce it by design. For example, through lower forces or removing trap point. Then the step 2, technical protective measures. Guard, interlock, light curtains for the risk that design cannot remove. Step 3, information for use. Warnings, trainings, instructions. Only this order is acceptable. You can never paper over a design flaw with a warning label. Chapter 4 covers safeguard in detail. Physical guard are specified in ISO 14120. Fixed guard where access is rarely needed, and movable guard where operators interact with the machine. A movable guard needs an interlocking device, and those governed by ISO 14119. This, this standard classifies the interlock types and pays special attention to the defeat prevention, because it because in real factories operators do not bypass switches with spare actuators or tape. Coded actuators, especially RFID based one, makes the manipulation much harder. The chapter also covers the emergency stop function as per the ISO 13850. Always remembering that an e-stop is a complementary measure, never a substitute for a proper safeguard. When physical guards obstruct the process, think of a loading a press. We use electrosensitive protective equipments or ESPE governed by IEC 61496. Light curtains and light grids creates an invisible sensing field. Interrupting it triggers a safe stop. Laser scanners protect areas rather than planes, which makes them useful around the robots and driverless transport system. And cameras base in a system, the cameras based system can ever surprise three-dimensional zone, pressure sensitive mats and edges covered by EN ISO 13856 detect a person by weight or by a contact. The right choice depends on the application. Fingers and hand detection needs fine resolution, whereas guarding tolerance and resolution demands clever zone design. A light curtain only protects if the machine can stop before hands arrive at the hazard. That is why positioning is a calculation defined in EN ISO 13855. The minimum distance S equals K times T plus C, where K is the approach speed of the human body, T is the total stopping time of the entire system, and C is the intrusion allowance that depends on detection capability. For a hand approaching perpendicular to a sensing field, K is typically 2000 millimeter per second. Its com its com its companion standards EN ISO 13857 defines the safety distance against reaching over, around, or through protective structures. Together, these standards turn safety placement from guesses into engineering. Chapter 5 brings us to safe control technology, my favorite part as a control engineer. EN ISO 13849 evaluates the safety related part of the control system using the performance level PL through PLA through E, where E represents the highest risk reduction. The required level PL comes from a risk graph considering the severity of injury, the frequency of exposure, and the possibility of avoidance. The achieved PL then depends on four ingredients: the architectural category from B up to 4, the mean time, the dangerous failure of the component, the diagnostic coverage of the tests built into the system, and the measure against common cause failure. Tools like Pilz safety calculator, Pascal automate this mathematics. The parallel route is IEC 62061. The machinery sector implementation of the functional safety umbrella standard IEC 61508. Instead of performance level, it works with a safety integrity level SIL 1 to 3 in machinery. So the philosophies coverage both quantities and the probability of a dangerous failure. And the compendium points out that their observation and mathematical principles are very simple. As a rough correspondence, PLC maps to SIL1, PLD maps to SIL2, PLE to SIL3. Both standards are harmonized under the machinery directives. So either route grants presumption of conformity. In practical, the choice often depends on the technology involved and on a company tradition. How it all this implemented in hardware. The compendium presents an evolution. For simple machines, safety relays like a classic Pilz PNOS monitor and emergency stop are argued with safety switch using a forcibly guided contacts. As the number of safety function grows, configurable smart controllers like PNOS multi-replace whole bundles of the relay with a graphically controlled logic. And for complex distributed plants, programmable safety controllers and automation systems like PSS 4000 merge safety and standard controls in a single environment. But whatever the platform, and ISO 13849 requires validation, proving by analysis and step-by-step testing that every safety function actually performs exactly as it was designed. Chapter 6 asks what happened when safety signal must travel over a network. A standards field bus along is not sufficient because transmission can fail in well-defined ways. Message can be repeated, lost, inserted, delivered in the wrong sequence, corrupted or delayed. Safe communication protocols add defensive measures on top: consecutive numbering, time expectation with acknowledgement, sender and receiver identifiers, CRC checksum. This all follows the black channel principle. The transmission medium itself is untrusted, and safety is ensured entirely the protection layer at the endpoint. In line, these are basically in line with IEC 61784. Pills on history here includes safety bus P and later the Ethernet base safety net P. To summarize part 2, risk assessment under ISO 12100 is the compass, and the 3 steps method is the route: design first, safeguard second, information last. Safeguard range from the fixed guard and coded interlock to light curtains, scanners and pressure sensitive mats, and standards like ISO 13855 makes their placement a precise calculation. Safe control technology qualifies reliable through performance level and safety integrity level to harmonize route to the same goal. And a safe communication extended that integrate across networks using the black channel principle. In part 3, we'll cover the safe motion and drive integrity of the safety function like STO and SLS plus mechanical, pneumatic and hydraulic design. See you there.